Okay, I will start. Hello, everyone. I am Xiang from the University of Technology, Sydney. I am very glad to introduce our work, Semi-supervised credit card for detection via attribute-driven graph representation. I'm going to introduce our work by 4 parts. Firstly, the background, then follow methods and experiments, and finally, several conclusions. Credit card fraud is an important issue and incurs a considerable cost for both cardholders and issuing institutions. Global card fraud losses amounted to over 30 billion US dollars in 2022 and is forecast to continue to increase. This huge amount of losses has increased the importance of fraud fighting. This figure shows a typical fraud detection framework deployed in a commercial system. The card alliance or bank assesses each transaction with an online predictive model once it has passed card checking. Unlike a simple card checking system, which focuses on card blacklists and budget checking, the predictive model is designed to detect fraud patterns automatically and produce a fraud risk score. Investigators can thereby focus on high-risk transactions effectively. We summarize the following 2 major observations from real-world fraud transactions. First, the label data is expensive. The number of fraudulent transactions is much less than legitimate ones. Therefore, it's difficult to achieve satisfactory performance through supervised methods. Second, there are many categorical attributes for each transaction, such as card type, card issuer, merchant type, and terminal type. Although these attributes are heterogeneous and noisy in the real world, they also can help us find more fraud patterns. Currently, many existing models are proposed for fraud detection. However, many of these methods require manually constructing features before feeding into a classification model, which fails to automatically learn the joint impact on temporal patterns and risk propagation. Our model can automatically value the transaction importance through the feature learning layer and attention mechanism. Moreover, to uncover the hidden fraud patterns, we introduce a risk propagation and temporal attention mechanism to capture intrinsic relationships among transactions. Next is our proposed method. We first have a look of the main framework of our proposed GTAM. Then we will introduce each component. The first part is the generation of a temporal transaction graph, which builds dynamic relations for transactions. Specifically, we have 3 steps to directly model the relations of transactions based on historical data and represent them in a temporal graph. After obtaining the transaction graph, we leverage attribute learning layer to encode the heterogeneous categorical attributes, which is illustrated in the right figure. In this part, we aggregate the representation of each attribute to encode the card, transaction, and merchant. Then we update each transaction's representations by aggregating information from their neighbors in the temporal transaction graphs in 2 steps. The first step is a heterogeneous attribute aggregation. The second is a time-aware graph attention mechanism. The right figure shows the gated temporal attention networks, which adaptively calculates the importance of the neighbors and aggregates the information according to the neighbor's importance. We also inject the label as one of the categorical attributes and give the mask to avoid label leakage. After the graph neural network, we leverage a multi-layer perceptron to give the prediction of each transaction's risk score. Next is our experiments. Our experiments are conducted in both the supervised fraud detection datasets and a semi-supervised dataset. The historical data has 10 million transactions, and we contribute a new large-scale partially labeled credit card fraud detection dataset to the research community, namely financial fraud semi-supervised dataset. Then we compared our proposed method with baseline methods and state-of-the-art methods. Besides, we used 3 popular evaluating metrics to comprehensively evaluate the classification performance. We evaluate the overall performance of fraud detection, which is the main task of this work. The first 5 rows of the table show the performance of baseline models. It is clear that none of these 5 methods are satisfactory, and their performance is all lower than that of other baselinesses. Lines 6 to 9 of the table show the performance of current state-of-the-art methods. According to line 9, PCGNN's performance is competitive. This proves the effectiveness of addressing the problem of the small proportion of labels. According to the last row of the label, our GTAN outperforms all baselines and proves the superiority of our proposed graph neural network in fraud detection. To further evaluate the performance of our model in semi-supervised experiment, we changed the ratios of label data during the model training period. We report the AUC score of our model and other models in this figure. Due to space constraints, we select some representative baselines to compare with our model. We can observe that our models stay ahead of other methods, no matter how many ratios of labels. The proposed model contains some key components, and we verify the effectiveness by evaluating each component, respectively. Specifically, we evaluate 2 variants, namely GTAN-A and GTAN-R. In the A model, we remove the TGAT component, and the central node aggregates messages directly collected from neighbor nodes. In this case, we obtain the transaction embeddings from all the neighbor embeddings with the same weight instead of adaptively adjusting the weights of neighbor nodes. In the R model, we remove the risk embedding component and only use the original node attributes. The gray bars in the right figure show the removal of the attention mechanism has the greatest impact on the accuracy metrics of the model. This proves that the reweighting of temporal transaction neighbors from the temporal graph attention mechanism is effective in our graph-based methods. Besides, the green bars in the right figure gets the second highest scores compared with GTAM, which proves that the risk embedding is effective in modeling credit card fraud patterns from transaction risk propagation. In summary, removing either component deteriorates the performance of GTAM, which proves that the temporal graph attention mechanism and risk embedding are both effective in graph-based fraud detection. Next, we summarize our contributions. First, we propose a graph learning framework to effectively model the relationship among the transactions for fraud detection, which fits the real-world fraud patterns. Second, we design a temporal graph neural network model to learn the transaction representations by attention mechanism and gated residual mechanism. The proposed model is concise and effective in joint and automatically learning from features and labels. Third, our proposed GTAN is interpretable and can be easily implemented in the industry-level system. Extensive experiments on both the financial fraud detection dataset and public fraud detection datasets demonstrate the superior performance of our proposed methods. That's all my presentation. Thank you very much for your listening.